the cell potential of the following reaction in volts if now we have a specific concentration of our ions. And the equation here is going to be that the cell potential equals the standard cell potential minus RT over NF ln Q, where Q is our reaction quotient. And let me just make sure. Yes, good. Okay, so our process here, if you remember our reaction quotient is the exact same form as the equilibrium constant, except given any random set of concentrations. So our Q will be product raised to coefficients, ignoring solids and liquids, but just solids in this one, divided by reactant raised to coefficient, but it's just a 1, so we don't need to write it. So our reaction quotient has come back to us. And all of the other characters still have the same meaning: number of electrons, Faraday constant, R is our 8.314, same as our last one. But we need to figure out our standard cell potential using our SRP table. This time, oh, this is interesting. We have silver going to silver plus as our oxidation. And if you're ever in doubt as to which one you're looking for, write it exactly as it occurs on your sheet. So the fact that there's a 2 here and that I did not write the 2 here, I'm going to have to put that 2 in eventually, but write it exactly as it appears on the sheet with its exact cell potential. And since I'm writing it backwards, I have to change this sign, minus 0.80. Now let me zoom back out, do our reduction. Pb2 plus needs 2 electrons to become lead solid. Our reduction potential here, again from our sheet, minus 0.13 volts. Now a couple things. So first off, this is the first time we've ever run into a cell potential that was negative. We get minus 0.93 volts. That's fine. It just means it's not a voltaic cell. There's one other kind of cell that's coming up, and that's called an electrolytic cell. Electrolytic cells have cell potentials which are negative. So I'm just going to write that here so that you'll be able to reference this when you get to those homework questions. This is an electrolytic cell because the cell potential is negative or less than 0. Now also, we see 2 electrons here. We need to do 2 electrons for the top. That means that n equals 2. And now we have enough information to plug in and solve this problem. Our E cell is our standard cell potential, which is minus 0.93 volts. Plugging in all our terms here, 8.314. Joules per mole Kelvin. It doesn't give us our temperature, so you may assume it's 298 Kelvin, which is assumed to be room temperature. N is 2. The Faraday constant is 96,485. Sorry, that's coulombs. And our Q is going to be our concentration of silver ions squared. Over just concentration of our lead. And now we've got all of it together. We can go ahead and solve this. I'll do my natural logarithm term first by doing the multiplication first. We have 0.00467 squared divided by 0.432. And then take the natural log of that. Yeah, that makes sense. Then multiply it by all these terms. I said this makes sense. See how it's a minus number? That's because we have larger concentrations in the denominator. I'm going to take this minus term, and there's another minus here, so this does in fact become a positive part. And then I'm going to multiply it times all this stuff, times 8.314 times 298. Oh, sorry, I screwed that up. All right, let me try that again. 0.00467 squared divided by 0.432. Take the natural logarithm times 8.314 times 298 divided by 2 divided by 96,485. And I haven't put in my minus sign yet. I then put in my minus sign. I get 0.127 or 0.13. So we get 0.93 plus 0.13 for a negative 0.80 volts as the cell potential for this process. And the idea behind this is that generally, to get a good idea of what your cell potential will be, pick your half reactions. But then even once you pick your half reactions, the concentrations can have a relatively significant effect, although it's typically smaller than the cell potential under standard conditions. Any questions about that?